Hello students and welcome to Chemistry B. I'm Ms. Slate and today we're going to talk about acids and bases. So first off, let's look at some common examples of acids. So hydrochloric acid, HCl, is the acid that's in your stomach that dissolves food. Sulfuric acid, that is like the kind of acid you're going to find like in a car battery, H2SO4. Vinegar is also an acid, that is specifically acetic acid. And carbonated water is also acidic because when you dissolve carbon dioxide into water, it forms carbonic acid. And what you can see is that all acids will dissociate when they're dissolved in water because acids are ionic in their character. So some properties of acids. Acids are molecular substances that will ionize in water. So acidic solutions will conduct electricity because they separate into ions when they're dissolved in water. They will react with active metals to produce hydrogen gas. So a common reaction is to put zinc metal in hydrochloric acid, and the products are hydrogen gas and zinc chloride. Acids tend to taste sour. So think of things like vinegar or the citric acid that is in citrus fruits. And they will change the color of acid-base indicators. So for example, if you have litmus paper as your indicator, an acid is going to turn litmus paper red. And acids will neutralize bases. And the technical definition, or at least one of the technical definitions for an acid, is a substance that produces hydrogen ions when dissolved in water. So anytime we have an aqueous solution of an acid, you're going to have H plus or hydrogen positive ions. So let's talk about naming acids. First off, it depends on what type of acid it is. We're going to start by talking about binary acids. Binary acids are ones that are made of hydrogen and just one other element. So you're going to take the root of whatever the anion is, add the prefix hydro to the front, and change the ending to IC, and add the word acid to the end. So for example, the negative ion in this first one is Cl, that's chloride. So chlor is the root of the anion name. We added the prefix hydro and changed the ending to IC. So it becomes hydrochloric acid. Same thing with our second example. The P-3 ion, phosphide. So when it becomes the acid, we use phosphor as the root of the anion name. Add the prefix hydro and change the ending to IC, hydrophosphoric acid. So pause the video for a second and try writing the name for HF and the formula for hydrosulfuric acid. All right, let's check how you did. So HF, fluoride is the anion, so we use the root name fluor. Add hydro to the front, change the ending to IC, hydrofluoric acid. To go the other way, hydrosulfuric acid, we're looking at the anion from sulfur, so that's sulfide. Well, sulfide has a -2 charge, so we would need 2 hydrogens to cancel out the charge on sulfide. So H2S would be the formula for hydrosulfuric acid. The other type of acid are oxyacids, which an oxyacid is just hydrogen combining with an oxyanion. So we're still going to use the root word of the anion for the acid name. The ending of the name, though, changes depending on what type of anion it is. So if the anion ends in ate, ATE, you change the ending for the acid to IC. If the anion ends in ITE, ite, you change the end of the acid name to OUS. And of course, add the word acid to the end. So for example, if you have chlorate as your negative ion, it becomes chloric acid. But if you have chlorite as the negative ion, it becomes chlorous acid. Just like if we have hydrogen combining with sulfate, that becomes sulfuric acid. But if we have hydrogen combining with sulfite, that becomes sulfurous acid. So pause the video for a second and see if you can figure out the anion name, and acid name or formula for these two examples. All right, let's see how you did. So HNO3, that is the nitrate ion. If the oxyanion ends in ATE, that means it becomes nitric acid. If we're looking at chlorous acid, OUS means that the anion must have ended in ITE, so we're looking at chlorite, which means our anion is ClO2 with a -1 charge. So the formula would just be HClO2. Now let's talk about bases. This is kind of the other side of the coin from acids. So sodium hydroxide is a common base. You'll find it in drain cleaner or oven cleaner, NaOH. Same with potassium hydroxide. It's often used in making soap, KOH. Magnesium hydroxide is an antacid, commonly known as milk of magnesia. And calcium hydroxide is used in wastewater treatment, CaOH2. And you'll also note that all of the bases also dissociate in water. Again, because they're ionic. So some properties of bases. Similarly to acids, they will also conduct electricity because they dissociate when dissolved. Solutions of bases tend to feel slippery, think of like soap, and taste bitter, again, also think of soap. They can emulsify fats and oils as well, and they also affect the color of acid-base indicators. For example, if you're using litmus paper as the indicator, a base will turn litmus paper blue. And bases can neutralize acids. The formal definition of a base that we're going to be using in this class is a substance that can produce hydroxide ions when dissolved in water. So when you dissolve a base in water, you're going to get OH negative ions in the solution. Now let's talk about the pH scale, because the pH scale is kind of how we measure acidity and basicity. So 7 on the pH scale means something that is perfectly neutral, okay? Neither acidic nor basic. So like pure distilled water is going to have a pH of 7. pHs less than 7 are going to be things that are acidic. And the lower the pH, the more acidic it is. So something like milk is slightly acidic, but battery acid is very acidic. Anything with a pH higher than 7 is going to be basic. And again, things that are basic are typically cleaning products. The other thing to remember about the pH scale is that it is logarithmic, okay? So stomach acid is not 1 times more acidic than a soft drink, the difference from 3 to 2. It is 10 times more acidic than a soft drink, stomach acid is. So every change of 1 on the pH scale is a factor of 10. And again, we can tell that because, again, it's based off the concentration. So you can see 10 times the concentration of hydrogen is 10 to some prefix. There's also what we call the POH scale. So the POH scale is kind of like the reverse of the pH scale. So 7 is still perfectly neutral, but the lower the number, the lower the POH, the more basic it is, and the higher the POH, the more acidic it is. So, like I mentioned before, the pH scale is a logarithmic scale to express the strength of acids and bases. Each step represents an increase or decrease by a power of 10. So something with a pH of 4 is not 1 times more acidic than pH 5. pH 4 is 10 times more acidic than pH 5. So this is how we calculate pH and pOH, and you're going to want to make sure that you have a scientific calculator that can do logs. pH is just the negative log of whatever the hydrogen ion concentration is. pOH is the negative log of whatever the hydroxide concentration in the solution is. And for a particular solution, if you add the pH and the pOH, it should always equal 14. And again, remember when we're talking about H plus in brackets, that's the concentration of the acid. And when we're talking about OH negative in brackets, that's the concentration of the base. So let's do some practice problems. So this one says calculate the pH and pOH of a 0.0075 molar solution of HCl. First off, if we're talking about HCl, that's hydrochloric acid. So this concentration is equal to the concentration of my hydrogen ion. So the first thing I'm going to do is calculate my pH, which the pH would be the negative log of the hydrogen concentration, which in this case is 0.0075, which comes out to a pH of 2.1. If I want to find the pOH, the easiest way to do that is to just do 14 minus pH. Because again, pH and pOH should both add up to 14. So when we do 14 minus 2.1, we get 11.9 as our pOH. Question number 2 says calculate the pH and pOH of a 0.00316 molar solution of potassium hydroxide. Potassium hydroxide, OH, that is a base. So this concentration right here is telling us the concentration of the base. So the easiest way to start this problem is to start by calculating the pOH first. Because pOH is just the negative log of our hydroxide ion, which in this case would be the negative log of 0.00316, which comes out to a pOH of 2.5. To find pH, we're going to use the same process that we used to find pOH in the previous problem. pH is going to be equal to 14 minus pOH. So 14 minus 2.5 comes to a pH of 11.5, which this should make sense for the pH because high pHs correspond to basic solutions, and we know potassium hydroxide is a base. So take a minute now to pause the video and see if you can calculate the pH and pOH of a 0.0312 molar solution of nitric acid. All right, let's see how you did. So we're given the concentration of the acid. So the first thing I did was calculate pH by taking the negative log of 0.0312, which comes out to a pH of 1.5. To find the pOH, I'm just going to do 14 minus the pH. So 14 minus 1.5 gives me a pH of 12.5. So just like we can use concentration to find pH and pOH, we can also go in the opposite direction. So if we need to calculate the concentration of hydrogen or hydroxide, the concentration of the hydrogen or the acid is going to be equal to 10 raised to the negative pH power. And the concentration of the base or hydroxide is going to be equal to 10 raised to the negative. So let's look at some example problems. This one says calculate the hydrogen concentration of a solution with a pH of 3.5. So to get the concentration of the hydrogen ion, I'm going to take 10 and raise it to the negative 3.5 power. And I get a concentration of 3.2 times 10 to the negative 4th molar. Number 2 says, calculate the hydroxide concentration of a solution that has a pH of 9.5. Well, first off, remember pH is going to give us the concentration of the hydrogen ion. If we want the concentration of the hydroxide ion, we need to figure out pOH. So the first thing I do is I calculate the pOH from the pH. 14 minus pH will give us pOH. So 14 minus 9.5 comes out to 4.5. Once I know the pOH, I know that the hydroxide concentration will be equal to 10 to the negative pOH power. So I take 10 to the negative 4.5 power, and I get a concentration for hydroxide of 3.2 times 10 to the negative 5th molar. Now take a moment to pause the video and see if you can figure out the hydroxide concentration in number 3. All right, let's see how you did. Again, they want hydroxide concentration, but they're giving us pH. So the first thing we're going to do is we're going to figure out the pOH. 14 minus the pH of 12.3 gives us a pOH of 1.7. Once we know the pOH, then we can determine the concentration. So 10 to the negative 1.7 gives us a concentration of 0.020 molar. And that concludes our discussion of acids and bases. Remember, important things you're going to have to be able to do is write the names and formulas for acids. You're going to need to know the basic properties of acids and bases. You're going to need to be able to calculate pH and pOH, as well as calculating the concentration of hydrogen and hydroxide ions present in a solution.